All right. Hi, everyone. Welcome to today's Friday Transportation Seminar. My name is Jenny Liu, and I am an associate professor in the School of Urban Studies and Planning, who I host this seminar today with Dr. Chris Monsere in Civil Engineering, and I will be introducing and moderating today's seminar. So our Friday Transportation Seminar has been a tradition since 2000. These seminars are usually held on Portland State's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, Guatemala bands of the Chinook, and the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. So it's important for us to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember those communities, and honor their legacies, lives, and descendants. So due to the COVID-19 pandemic, today's seminar and the rest of this term seminar will be hosted online fully. And today, we are very happy to have Chris Monsere, Dr. Chris Monsere, Dr. Sirisha Kothuri, and also Dr. David Hurwitz here presenting on an assessment of bicycle detection, confirmation, and countdown devices. So Dr. Monsere is a professor of civil and environmental engineering and associate dean for academic affairs in the Massey College of Engineering and Computer Science at Portland State University. Dr. Monsere's primary research interests are in design and operation of multimodal transportation facilities using user behavior, comprehension, preferences, and the overall safety effectiveness of transportation improvements. Dr. Monsere is also a member of ANF 20, the Bicycle Transportation Committee, the past co-chair of Transportation Research Board's Safety Data Analysis and Evaluation Committee, and a past member of the TRB Task Force to develop the Highway Safety Manual assessment of, And then I would also like to introduce Dr. Sirisha Kothuri. She is a senior research associate in the Department of Civil and Environmental Engineering at Portland State University. Dr. Kothuri's primary research interests are in the areas of multimodal traffic operations, bicycle and pedestrian counting, and safety. Dr. Kothuri is the research co-chair of Transportation Research Board's Pedestrian Committee and the Bicycle and Pedestrian Data Subcommittee, and a member of the Traffic Signals Systems Committee. She received her BCE from Osmania University in India and her master's degree at Louisiana State University and PhD from Portland State University. And last but not least, Dr. David Hurwitz is a professor of transportation engineering and director of the Driving and Bicycling Research Laboratory in the School of Civil and Construction Engineering at Oregon State University. David also serves as the Associate Director at OSU for the Pacific Northwest Transportation Consortium, PACTRANS. David conducts research in the areas of transportation, human factors, traffic control, transportation safety, driving and bicycling simulation, and engineering education. In particular, Dr. Hurwitz is interested in the consideration of user behavior in the design and innovation of transportation systems. So before we get started, wanted to highlight some of our upcoming webinars and seminars. So for the next couple of weeks, these are the topics that are up here. And they're all very exciting topics. So we invite you to check out the NHTSA Trek website for more details. And also wanted to highlight an in-person event, the Fall Mixer for PSU transportation students on October 13th on the rooftop of the Urban Center building next Wednesday from noon to 1 p.m. And we're looking forward to connecting with currently enrolled PSU transportation students, staff, and faculty during this outdoor event. And there should be a RSVP link in the chat that will be put up shortly, if not already. All right. It is up there. All right, so for those of you who are attending this seminar as a class, make sure that you note which class section you're enrolled in. So as an overview of today's seminar, you can expect our speakers to present for about 40 to 45 minutes, followed by a Q&A. And as noted on the slide, please type your questions in the Q&A on the Q&A button that you'll be able to press on your Zoom session. So we will be asking the presenters these questions at the end of the presentation. And in case we don't have time for all of the questions, we will then send our speakers any additional questions to potentially answer via email if they are able to. And closed captioning is enabled, and you'll just have to click on the CC feature on your control panel to see it. And also just to note that this will be a recorded webinar and it will be available on our website later today along with the presentation slides. And finally, there is a 1 hour of continuing education credit for professional development. And finally, with that, I will hand it over to our speakers.
Great, thanks, Jenny, for the introduction. Get my Zoom panel organized here. So welcome. We're excited to share with you the results of our research project and other successful collaboration between our 2 research labs at Oregon State and Portland State. So just as an introduction, if you approach this intersection here and you can see the big red dot, meaning there's a red signal, and you're in a vehicle, and this signal has what's called actuation or detectors. When you pull up as a vehicle, you really don't have to think about where you're going to stop so that the signal knows you're there. In this case, this intersection in Oregon, the detection is done by inductive loops, and they sense change in inductance caused by metal objects, and cars are very big and the sensors are sensitive enough that the car doesn't really have to think about where it's going to wait for the sensor to go, a car is here, and essentially start the logic in the traffic signal controller about when you are going to get the green signal as a car. When you're a bicycle, you have a lot of choice about where to wait. We try and provide some indication about where you should wait so you could be picked up by these sensors, and you'll see this on the next slide with these markings on the pavement. So as a bicycle, there's kind of 2 options for setting up the detection. One is a specific waiting location, like I indicated on the slide before, and either with different technologies, loops, video zones, or even if we provide a push button, you're required to wait in that space and do some action, place your bike in the right spot in order to get the detection. Now, there are some technologies that are smart. We've got thermal video, we've got some radar. There are some work that actually David and his colleagues at University of Oregon have been working on in connected bike infrastructure. So there are some location detection strategies that don't require the bike to wait in a specific location. But in general, the vast majority of detections require the bike still to wait in a specific location. So as a bicyclist waiting, one of the things you don't know that you've been detected by the traffic signal on bicycles. If they're not in the right place, they have to wait basically a much, much longer time before they get a green indication, sometimes to the point where they have to take action and cross the road without the signal indication. So the benefits of providing some confirmation of detection is that, one, in a long sense, people would learn where to wait to be detected. They would presumably, by doing that action, they would incur less delay. There could be potential improved compliance with the traffic signal. But really, one of the main benefits is better experience waiting for the green. So there's a little bit less anxiety knowing that you've been detected by the traffic signal and are ready. It knows you're there, basically, and you're going to get service. There are some examples. This sign and detector is available from a vendor in the US, and there are a few locations that are using it. In the international sense, these, person scale Nearsight small bicycle signal heads with both an embedded sort of detection confirmation and a countdown timer that tells you how long to wait to green are commonly used. This is one where it's a numerical countdown timer. Then our colleagues in New Zealand sent us some examples of push button detectors that, with the waiting, right at the waiting rail for the bicyclist to push the button, and the device provides positive feedback that call to the traffic signal has been acknowledged. We do have some parallel with the pedestrian signals. The countdown timer for pedestrian signal is widely applied here in the US, but it's counting down it's not counting down the time to green, it's counting down right the time you have left to clear the intersection. And there are some head push buttons that also sort of provide positive confirmation that the call has gone into the traffic signal. Here in Portland, Peter Kuntz at the City of Portland sort of pioneered this use of this blue light that sort of provides feedback to the bicyclist that the signal has basically the sensors have detected you. And there's some examples of it being deployed in Austin. This is about 8 years old. And then some more recent photos in Salem with some combination of sign and a different placement of the blue light. So our research objective was to take a look at some alternate designs for detection confirmation devices and see how well they are understood by the general public, using some quantitative information from surveys and field reviews, and also try and get a sense of how well these devices provided a better experience for the cyclist waiting, and then ultimately, like all of our work, is to provide guidance on how to use these. So I'm going to turn it over to David, Sirisha, to talk about our methods.
Okay, great. Thanks, Chris. So our research methodology essentially followed a mixed methods approach, and it consisted of 3 main steps. First, we conducted an online survey, and the objective of this survey is to understand the general public's comprehension of these blue light detection confirmation systems, both with and without sign, as well as the countdown timers. Next, we conducted video data collection in the field, and the objective here was to compare cyclist behaviors both before and after these systems were installed. And we tested a few different versions of the blue light devices and one Nearsight countdown timer, and I will be talking more about that shortly. And finally, we conducted an intercept survey of cyclists at the locations where these field devices were installed. And the idea there was to elicit cyclist comprehension of these devices, and also to get their attitudes and preferences for these devices and how visible they were out in the field. Okay, I will be talking more about each of these approaches. Next slide, please. Okay, so the first step in terms of the online survey was for us to develop a generic template for the survey images. And we decided to go with the Google SketchUp image, as you can see here, instead of a real photo, because that gave us more flexibility to explicitly modify the scene. And we made every effort to present these questions neutrally, so that the respondents can provide more meaningful answers to the questions related to the comprehension of these devices. We undertook several rounds of refinement and review of these questions and tested the survey before we sent it out. The survey essentially consisted of 21 questions, which were a mix of both open-ended and closed-ended questions, and it was administered via Qualtrics. And so essentially the survey design consisted of 2 branches, especially for the blue light device questions. As you can see here, one set of questions was presented from the bicyclist perspective, as you can see in the left-hand side, the image here. And the other set of questions was presented from the driver's perspective, and which branch the respondent saw was randomly chosen. As part of this survey, we were also testing the need for additional supplemental signs for the blue light confirmation devices. Next slide, please. Another thing that we also were testing in the survey was the comprehension for the bicycle countdown timers, as well as the respondents' preference for the different configurations that you can see in the image here. So we have the numerical countdown timers, we have the circular dots that disappear and indicate the time remaining until green indication, as well as the vertical disappearing dots. Next slide, please. So in terms of recruitment for the survey, we conducted it in two ways. The first was via postcard. We purchased a random sample of over 10,000 addresses that were weighted, and these postcards were then sent out to these addresses. These postcards contained a link for the online survey. And in order to increase participation, we offered incentives in the form of a drawing to be conducted for some Amazon gift cards. And so the respondents, after they completed the survey, could choose to enter their contact information to be entered into this random drawing where they could win these gift cards. We had 568 respondents access the survey, and we ended up with 529 usable responses. So that yielded a response rate of 5.8%. The other recruitment was done via social media through an ad placed on Facebook. And these ads were targeted to both people in Oregon as well as people in the US only. And we had over 1,500 people click this online link, and we ended up with 535 respondents who actually completed the survey, and that gave us the responses that we analyzed further. Okay, next slide, please. So then we took those responses, and then we also looked at some differences between the samples that were obtained from the postcard as well as from the online Facebook social media. So based on the sample from the postcard, we found in general that the postcard respondents were older, and the age groups of 55 to 64 and 65 plus were overrepresented in the survey sample, along with being male and being white. In the social media surveys, we saw overrepresentation in the 25 to 34 age group, so no surprise there. We also did see some differences in terms of cycling behavior and trip types. So for the sample in Oregon that we obtained via postcard, we saw that those respondents reported that they cycled far less than 5 miles per week in comparison to respondents from Oregon obtained via social media. We also saw that the respondents from Oregon that were drawn using the postcard method reported that they cycle less for either fun or exercise in comparison to respondents from Oregon drawn from the social media or even the national sample itself. Next slide, please. Okay, so next for the field video data collection, our objective here was to compare and see if there was any change in the behavior of persons on a bicycle, so with respect to their arrival location, so where they're arriving at the intersections, their compliance, as well as stopping position. And this was done both before and after these devices were installed in the field. And in the field itself, we tested two types of far side blue light feedback confirmation systems that you can see here. The first design that we tested was where the blue light is embedded as part of the sign. And so the blue light itself is dynamic, so it goes on and off, but it is embedded in the sign itself. The second design that we tested was where the blue light was in the back plate of the signal head itself. And then there was a static sign that was present like right next to the blue light. And the sign itself did not change. So one thing to mention here, as Chris pointed out earlier, is that the blue light in the back plate has already been in use in Portland over the last couple of years. And so what this study was essentially testing is that the addition of that supplemental signage next to that blue light. Okay, next slide, please. So these far side devices were tested at 4 different locations in Portland. And these are pictures of the 4 locations. So the first one was Ainsworth Street westbound at North Interstate Avenue. This was a shared approach for both bicyclists and vehicles. And there was a pavement marking that here that cyclists could position themselves on in order to get detected at the intersection. There's also a push button that is right next to the curb. And so at this location, cyclists did use that push button as well instead of positioning themselves on the stencil marking for detection. The second intersection was Northeast Grant Place at eastbound at 33rd Avenue. This was also a shared facility for bicyclists and cyclists. And this included that stencil pavement marking as well. At both these intersections, Ainsworth and Grant, the design that was used was the one where the blue light was embedded in the sign. So it's a part of the sign itself. The other 2 locations, 53rd Avenue southbound at Gleason Street and Terwilliger Boulevard southbound at Capitol Highway, had the far side devices where the blue light was installed separate from the sign. 53rd Avenue southbound was also a shared approach for bicyclists and cyclists. But the Terwilliger Boulevard southbound location was the only location which had an exclusive bike lane for bicyclists. It also had this waiting area that was denoted by green paint where the bicyclists could position themselves to wait for the signal to turn green. I also want to mention that at all these locations, these previously had the blue lights in the signal itself. And so for the Ainsworth locations and the Grant Place, that blue light in the signal was removed and replaced with the design where the blue light was embedded in the sign. And at the other 2 locations, the supplemental sign was added. And since the city of Portland was testing those devices previously, we obtained the before data from them that was collected in 2017 and 2018. And so as a part of this study, the data that we collected was after the supplemental sign was installed. The Eugene locations, there were 4 approaches at 2 intersections. So West 5th Avenue eastbound and westbound at Blair Boulevard, which are also shared facilities for bicyclists and vehicles. The Monroe Street northbound and southbound at West 6th Avenue were also shared facilities. And all these approaches had those pavement markings to indicate to the bicyclists where they should be waiting. since these locations did not have the blue lights installed previously, they were installed as a part of the study. And so at these locations, the design that was chosen was where the blue light was embedded in the sign itself. And so the before data was collected in September of 2019, and the after data was collected in October of 2019, both as a part of this study. So this is a sample video that shows how the blue light actually works in the field. And you can see here, as the cyclist approaches the intersection and they enter the detection zone, the blue light, which was off previously, turns on, providing that valuable feedback to the cyclist that they've been detected. And this particular location uses video detection, and therefore the detection zone is larger than what we would traditionally expect from an inductive loop, and therefore that's why the blue light comes on much more earlier than what you would expect if you used an inductive loop for detection. So we ended up with almost 2,000 observations of cyclists across all these different intersections. And we analyzed this data further to understand the operational characteristics, and David is going to talk more about the results shortly. The next design that we tested for the blue light system was a Nearsight installation. And this was where the blue light was embedded in the sign. So similar to the far side installation, but this is just placed near side. And this was tested at the intersection of Oregon 34 at 26th and Brooklyn Drive in Corvallis. This approach is also a shared facility, so bicyclists and vehicles share the lane. And one thing to note here is that there is this sidewalk bike path that is heavily used by cyclists at this intersection. However, for the purposes of the study, we just decided to focus on the on-street arrivals because they are in the best position to see the sign and react to that. As a part of this study, previously there was this old stencil marking that was towards the right end. During this testing process, a new stencil or pavement marking was added towards the center of the lane with that black background that you can see on the screen. So the before and after data for this location was collected between February 2020 through September of 2020. Next slide, please. Okay, the final device that we tested was this Nearsight countdown timer. And this was installed at the location of Broadway and Williams in Portland. And this intersection already had the far side and near side bicycle signal faces already. And so this countdown timer was installed right below the near side signal face. This countdown timer is the version where the circular disappearing dots indicate the amount of time that is left for the green indication to be displayed, and also includes the word stop. So very similar to the Dutch countdown timers that you saw previously. The one thing to note here is that there is a sign which does there's a no turn on red sign at this intersection, and that applies to bicycles as well. In addition, all the data that was collected was during the pandemic, so between May and August of 2020. Yeah, okay. So the intercept surveys, as I mentioned previously, were collected at all these locations, and postcards were handed out to the cyclists at these locations that I just described, where these devices had been installed. And these postcards contained an online link to the survey. The postcards also contained a code which allowed us to keep track of where, at which intersections the responses would be coming from. These intercept surveys were conducted in early fall, September. The blue light intercept surveys were conducted in early fall, September and October 2019. And the Nearsight blue light device and the countdown timer intercept surveys were conducted in September and October of 2020. Our response rates were between 31% and 69% across the different locations, with an average of about 45%. So once we obtained these responses back from the online survey and the intercept surveys, we had to come up with some coding criteria, especially to code those open-ended comprehension questions. And so the table here shows the criteria that we came up with to classify each response as correct, partially correct, or incorrect. For the scenarios where the respondents were asked to indicate what they would do when they saw the blue light at the intersections with or without signage, either with a car or bicycle, a response was coded as correct if they indicated that either the bicyclist or the vehicle has been detected at the intersection. It was coded as partially correct when the respondent recognized that the car or bike has been detected nearby, or they indicated that the traffic signal has been triggered. Any other response that they gave us other than these that are listed here was coded then as incorrect. For the countdown timer, we were looking for a response which indicated that the respondent recognized that either the dots or the number indicated the amount of time left for the cyclist to get the green indication as the correct response. If they just told us that the countdown timer was just used for traffic operations in the field, either for stop or go, that was deemed as a partially correct response. And all other responses were termed incorrect. And with that, I will hand it off to David to go over the results.
Thanks so much, Sirisha, for doing all the heavy lifting on our methodologies. So we'll go ahead and transition now into some of the key takeaways that Dr. Monsere and Dr. Kothuri, myself, and all the graduate students that worked with us extracted from that massive amount of data. These are a little bit information heavy, so bear with me for the next couple of slides. We'll start with answering the question, what are the rates of comprehension for these different traffic control device presentations? So on our vertical axis here, we're looking at all the different configurations that we implemented through intercept survey evaluation in the field, both near side and far side presentations with the blue light embedded in the backplate or in the sign itself, with the light being on or off, followed by the purely online survey responses. So some things that stand out to us as we look at the distribution of correct, partially correct, and incorrect responses, we have higher rates of correct or partially correct responses for those far side presentations. Recall, like Sirisha mentioned previously, that's the most similar to the way this technology has been implemented in Oregon historically. So as Peter and the PBOT team have tried this at intersections in Portland, that's where we've seen a couple of years worth of implementation. So slightly higher responses there. In terms of the comprehension rates for the near side presentations, these are going to be pretty sensitive to line of sight, the relation of where those devices are with where our subjects, the bicyclists in this instance, are positioning themselves. And so perhaps those particular locations didn't line up as clean as we would have liked. Okay, well, let's go ahead and turn our attention to the comprehension for the bicycle countdown timer in the next slide. So here we're thinking about comprehension rates for the countdown timer specifically. So that one case study application in the city of Portland. And we have 4 different sets of data that we're considering here. The Intercept survey conducted in the field, followed by our online surveys across social media in the country, in Oregon, and then the postcard responses in Oregon. And what we're seeing here are, generally speaking, similar distributions of responses as compared to comprehension rates for the sign configurations. The biggest difference is the share of partially incorrect responses has shifted a bit in these distributions. But combinations of correct and partially correct responses, similar comprehension rates to that of our sign presentations. Okay, next slide. So a couple of mission critical questions, we think, starting with, was the blue light or the countdown timer observed? So binary responses, did our survey respondents detect the presence of these devices? And again, we're focusing here on the Intercept survey. So these were folks that passed through a test site with one of these devices. Highest correct response rate that our site was detected occurred in Portland with that far side blue light embedded scenario. And the lowest rate of visual detection occurred in Corvallis for the near side blue light embedded condition. And I had mentioned this before, we suspect that's related to the placement of our users and the devices. And so if you think back to the images that Sirisha had walked you through, this particular approach in Corvallis is a very wide lane, and there's quite a sharp angle towards the presentation of the device. You might not have got a feel for it in the photo, but it's also an uphill approach, and our cross street is significantly super elevated. So there's some interesting geometrics happening at that location, might have made it tougher to detect that near side presentation. Okay, let's go ahead to our next slide. Big question number 2, were the blue lights or countdown timers clearly visible? And so here we're looking for percent of subject respondents who agreed or strongly agreed that the displays are visible, and the range of responses falls between about 52% to about 87%, either agreed or strongly agreed that the device's presentation was highly visible. And we're seeing slightly higher rates for those far side presentations in both Portland and Eugene. Okay, next slide. A pretty important one to us. This starts to get at the heart of one of our motivating factors. Are we appropriately enfranchising non-motorized system users at transportation infrastructure? And so did our bicyclists perceive that their waiting experience was improved by providing this additional bit of information to them on their approaches while they're waiting for the right of way? Here we're displaying data across both the online and the Intercept surveys for all of our different conditions. And again, we're plotting the rates of agreed or strongly agreed to the question, was your waiting experience improved? And so rates of agree or strongly agree range from about 58% to a high of about 82%. So this starts to become a pretty strong indication that folks felt benefit from being provided from this alternate experience as compared to having to contend with vehicle-centric detection like Chris had described in our orientation materials. Okay, next slide. Part and parcel with the perceptions of the experience itself, was the information deemed useful by our subjects? Did it help them increase their confidence that they were making correct decision-making for stopping and going, yielding the right of way, and so on. And here we see even slightly higher agree and strongly agreed responses, ranging between 72.4% all the way up to about 91%. And so there's overwhelming support that this information is useful in decision-making and behavioral response. So that's a positive outcome as well. Next slide. So here we're transitioning from some of the key takeaways from survey and open response data into our video analytics that Sirisha described. And so like she had mentioned, a couple of thousand observations of actual bicycles interacting with these systems around the state. And here we're presenting data from both our Portland sites as well as our Eugene sites. We're very confident that the context of the implementation, the characteristics of an individual intersection are influencing the behaviors we see. So we're segmenting these out. The installation sites in Eugene a little bit more similar to one another than, say, the sites in Portland. What we're plotting are the before and after behavioral observations for waiting location. So blue describes waiting positions before, green describes waiting positions after, and we're asking a question, are they lining up correctly with that stencil in the pavement? And so we'll start with the cleaner set of data coming from Eugene. We're seeing improvements in waiting position based on the presence of our device across all 4 test sites. So you can see that the correct position increases on the neighborhood of 10 to 15% per location. So that's an easy trend to explain. But of course, as with all field work, there's an infinite number of variables, and sometimes we see the context of a particular location influencing the outcomes. Portland's a little less clear. We have one site where we saw quote unquote improvements in the consistency of where subjects are waiting. That's at our Northeast 33rd Ave at US Grants. And then we have 2 locations where we saw reductions in the quote unquote correct waiting spot for our subjects. So less easy to extract meaning from that trend. But on average, globally, we saw improvements in the waiting position based on the inclusion of these devices in the field. Okay. Next slide. Waiting location in relation to our bicycle signal countdown timer device. Recall that's one condition in the city of Portland. We're plotting here before and after behavior, same sort of information. So blue is indicating waited in the street until the green indication was presented. And then that green plot is waited in the street initially, but ultimately ended up departing on red. And we need some caveats here for this particular location. And we think that this is one of those places where context plays a significant role. If you actually look at this particular location, a lot of the decision-making that we're seeing is bicyclists under very low volume scenarios during COVID observations, accepting gaps perhaps against a traffic indication. And so the distribution of waiting position before and after doesn't increase correct compliance, but this is confounded by volumetric conflicts. So they're accepting gaps for right turns here in the absence of all conflicting movements. So while not perhaps the right position, the consequences of that choice are debatable. Okay, let's go to our next slide. Here we're talking about change in compliance over time under our different conditions. And so there's a good bit of information, but what we're trying to emphasize is that the greens are shifts in yes, the subjects complied with the messaging that's being conveyed. And so we can take one example here of the Portland timer. And so we saw a decrease in initial compliance of 8% in green. And then when we turn to the blue, we're looking at a 1% shift in the turning on red without signage, and then a 7% shift in running the red light. And again, this particular location is going to be compounded by volumetric loadings under pandemic conditions and the availability of reasonable gaps influencing behavior. And so as the research team tried to make heads or tails of some of these different thresholds, in this particular instance, our traffic control device is not overriding the behavior of the context of that particular location. Desire to do things like conserve momentum when approaching a traffic light. Okay, with that, we can go ahead and transition to our concluding remarks, and Dr. Monsere is going to bring us home with a few overarching observations.
Thanks, David and Sirisha. Let me get rid of clear all the drawings. Okay, so our conclusions, that the blue light detection confirmation provides useful information for cyclists. So I think this is the primary conclusion of our work, is that that cyclists, persons on bicycles at these intersections, appreciated the confirmation that they had been detected by the traffic signal. We should have mentioned that the sign comprehension, or the comprehension information we showed, is for questions with the sign. We also sampled without the sign, and the comprehension was very low. So people, in absence of the supplemental sign, did not comprehend what the blue light was communicating to them. So that was one in the project. When we moved from the online survey to the field work, we used the results from the survey to sort of craft some different options for the sign. The folks at Eugene and Portland and the sign shops were very ingenious in embedding the blue light in the sign, which we thought was an addition to test. And I think we did see better sort of comprehension of that sign, most likely because all of the information is placed within one place when the person is glancing at the sign, everything's all encompassed. We do recommend separate detection for bicycles. I don't know if you would have caught early in some of our slides, we did show supplemental signs that showed a picture of a bike and a car, or that to indicate that the blue light is indicating any vehicle has been detected. The Austin sign that you noted said, vehicle detected. But a lot of the signals we were at, the loops, detected both bicycles and cars. So even if there was only a car there, the light would be on. And so it would take a little bit more to separate out that detection. The Corvallis location did function that way because the detector was able to separate cars from bike because it's a higher technology, sensor technology. So we would recommend that, or thinking about the sign to make it match the actual situation. We still, the phrase detected doesn't always, we've seen this before in prior work by others about communicating to people about what traffic signals do in terms of how they turn green. And I think we're still, detected might not be the best, but it seemed to, it did have relatively high comprehension. And we didn't have any wordsmithing options to make it better, but it's just worth noting that there are some people in the survey who still, aren't traffic engineering geeks like us and know what's going on in the signal box. So on the other hand, the countdown timer, both the one that we installed in the field and all the other options had high comprehension rates, were easily understood. People got the disappearing dots, what that meant, and had the highest comprehension rates. And so the countdown timer coupled with that detection piece is a possible, very valuable tool. We didn't expect significant changes in behavior, and we didn't see it. And I think the compliance question is one that we looked at, but if you want to read all of the messy details in the report, there's a lot of caveats to the changes in compliance. And I think the research team's conclusion was that the devices we were testing were not the primary influence of the change in compliance. So don't take too much away from those slides. The other thing is we did noted that, that most people are accustomed to looking far side for traffic information at a traffic signal. And then if you're the near side placement needs to just be a little, thought out better in the design. So we're not saying near side doesn't work or it's not an option, but and people's behavior and observations would change over time if more things were placed near side. It's, fairly common in many other countries in Northern Europe to place the bicycle information at scale near side. So, but currently we just observe that based on sort of US expectations. The usual limitations about stated preference surveys and the online sample, while we tried to get a representative sample, it still has bias about who will reply to those surveys. We didn't provide any non-English. I saw there was a question already in the questions. We didn't provide any non-English options to the survey. We didn't provide any non-computer access to the survey. So it has those limitations about who we are saying comprehended the sample or comprehended the survey. The intercept surveys, especially for the countdown timer, were small. If it wasn't a pandemic traffic situation, the traffic at that intersection is a lot, and we would have gotten a lot more cyclists to respond. But because of the traffic situation in August and September, the sample of people at the locations was low. So, and the two near side tests were delayed because of the pandemic. So we were about ready to do field work when things went into lockdown. And so it got pushed way out. So it does, some of the work does mix, pre-pandemic and post-pandemic for the near side signals and the near side presentation devices. And so that complicated our interpretations of some of the results. Really important to recognize that this was a project sponsored by the Oregon Department of Transportation through their SPR program, and Josh Roll was our ABLE project manager. The full report there is linked on the slides if you want to, as David mentioned, the trove of data that is in there. There's a lot more about sort of exploring the different device types and comprehension, and probably more ways than you would want to slice and dice it, but it's all in there. And then the two teams at the cities, Peter Kuntz and Oliver Smith and Andy Kading at the city of Eugene, were obviously key partners in terms of the field installation. So it's really nice to have a project where you do, survey, field work, change something, test it, survey. So this, of these devices, we really loved the ability to kind of close all the methods and sort of triangulate the results. And then lastly, just recognizing some of the graduate students who have moved on to Hisham Jashami is at Michigan State now, and Doug Cobb is in Florida, and Frank Apia is at WashDOT. So, but we thank them for their contributions. And so with that, we can open it up for questions. Thank you.
All right, thank you so much, Chris, Sirisha, and David, for this excellent presentation. There is so much data and information in there that I'm not sure that we were able to see most of it, because there's just so much that you're sorting through. So those of you who are on the webinar, feel free to continue submitting your questions in the Q&A button. And I see that our presenters have already answered a couple of those already. So I'm going to start with a question about whether or not the research team was able to assess the condition of the weighting on stencils, the stencils on the ground through the testing period, whether they were all identical and whether they were kind of all maintained in a similar condition. And the question asker also said that it was interesting that people may understand what the blue light means, but not necessarily how it's triggered.
Sirisha, do you want to? So I think, the stencil conditions and the changes in stencils was not the primary focus of the project. So we measured, just did the location change with the installation of the blue light and blue line sign. There has been quite a bit of other work looking at options for the stencils, including some work by the PBOT team, and there's a couple of at least TRB papers that are published, and they're cited in our reference list. So that question about where to place the stencil and how much different types of stencil options, there's some other work on that. It wasn't the focus of this project.
I'm tag teaming with my colleague, Professor Liu, helping to field the questions. There's a lot of good ones. There's one, did you consider a graphic or picture only type of sign instead of the text? Or do you think that might work, might improve comprehension?
I'll take that one. Great question. We're always looking to reduce the information loading on transportation system users. And so the distribution of sort of legend only versus hybrid symbol plus text versus text only was something that we debated back and forth. And we did our best to alpha test within students in our programs, some different sign configurations, and then shortlist stuff that was constructible by our agency partners, because we really felt strongly we wanted to put these technologies into the field and do a real world assessment. And so we're of course constrained by what folks might be willing to put into their roadway environments at their intersections. So we came back to this hybrid presentation as the best configuration that we could come up with. And Chris emphasized we still argue internally over how we could have improved on the word detection. That was the element that we had the greatest level of concern with.
Thank you. So I was wondering, there were some pretty significant differences in, I guess, the responses or correct responses to the signals, depending on whether you were doing the Intercept survey versus the online different versions of the survey. And I was wondering if you could maybe talk about how, why you feel like there were the significant differences, whether it was the population that was being sampled is quite different, or whether it was something else.
Let's see, I'll take the first crack, and then so I think the primary difference we sort of hypothesized is that the people that are intercepted surveys actually experience the device in the real, so most of them saw it, and probably at a lot of the locations, especially the Portland ones, had been seeing it for a long time. So they were familiar with it, and so I think that explains most of the differences. And I think what's interesting too is at the Eugene sites where this was brand new installation, the comprehension was still good and high for the intercepted survey people. But although we try our best with the Google SketchUp to create a situation that looks realistic, it's not. So, but you're muted, Dave.
You'd think after 2 years I'd have the button pushed down. Chris is spot on. I'd add two observations that come up in the technical report. When we start to look at the national based surveys in different parts of the country, lights with these colors at signals have some other interpretations. And we saw a little bit of that in our survey responses. They can be mapped to emergency response and enforcement designs at signals. So we got a few spikes in Florida around triggers for enforcing red light running and some other observations. So that can play a role, variability in traffic control device application nationally. So that's one. And then a second small observation would be there's some great reporting that has quite a bit of visibility in the city of Portland that had talked about these designs and their purpose, and some of our respondents had seen that stuff. More common for folks interacting with the Portland locations than say maybe the Eugene locations. So just public information and education influencing some of those comprehension rates, as well as a second confounding characteristics, adding to everything that Chris had already said.
I realized we just have 1 minute, and maybe you could quickly do this question. Did you look at all of whether the detectors could filter out detecting a bike versus a motor vehicle? Was that part of your analysis?
Not robustly in terms of the way we crunched data. Like Chris had been alluding to, and as Sirisha described as well, the before conditions in these locations were mostly inductive in-pavement loops, and those are in their current configurations not differentiating class of user. But as we move to more advanced technology, whether it might be a thermal-based sensor or a radar-based sensor, you can start to generate pretty high rates of differentiation. The Nearsight display that we used in Corvallis used one of those thermal type technologies. And so it's aimed center of lane, and it can differentiate a bicycle from a vehicle at pretty high rates of accuracy. And so those presentations look a little bit better and could influence the accuracy of the science description. So that's that newer tech refining that level of detection is on the horizon, and gosh, even implemented in the world today, which is pretty exciting.
All right. Thank you all to our speakers, Chris, Sirisha, and David, as well as everyone who is joining us today. That concludes our Friday seminar. So you will be receiving a brief survey after the seminar ends. And I hope that we appreciate your feedback to complete the survey. It just takes a couple of minutes, and we hope to see you all again in our future seminars. And thank you all for joining us. Have a great weekend. Thank you.